Okay, so this is the outline for chapter 23. So first of all, we will introduce electric flux. What is electric flux? And then the second outline is the Gauss law, which is the main part of this chapter. Of course, it is the title of this chapter. And then we will apply the Gauss law for calculating some structure, how the structure generates the E field. The first one is the charge isolated conductor, and then we will try to apply Gauss law for some symmetrical structure like cylindrical symmetry, planar symmetry, and spherical symmetry. Okay, so I will say in chapter 22, of course, we can use some integration to calculate the E field generated by some structure. But I will say that the mathematics is easier, but the calculation is more complicated. And here we try to use the surface integral, which means that the mathematics is more difficult, but it makes the calculation more easy. So this is the trade-off. You can either use some simple mathematics, but the calculation will be quite tedious for some structure. For some example, in the previous chapter, you need to do some integration. You need to separate the structure with some continuous charge distribution into many small segments, and then you try to do some cancellation of component, and then you try to do some integration. The calculation might be quite complicated, but here, if you would know the surface integral, then you can try to apply it for some symmetric structure. Then the calculation will become easy. Okay, so this is the overview for electromagnetism, which is the main topic in this semester. So, of course, in chapter 33, we will have a chapter called Maxwell equation. And here, this is a table about the Maxwell equation. Actually, in this textbook, the notation are not actually the same, so it doesn't really matter to care about too much about the notation. In this textbook, it's written as a integration of a E dot dA equals Q enclosed, something like this. Yeah, so how it is written is not that important because for different textbook, the equation are different. So here, this is just to let you know the overview. So the main target of this semester is to learn the Maxwell equation. And in this chapter, we will learn one of them, which is for the Gauss law for the electric field, or the electric version of the Gauss law. And here is also mentioned the point form in this textbook. It doesn't really tells you what is the point form or the differential form of the Maxwell equation. But in chapter 32, I will make it a supplementary note so that you will know the differential form, and then we'll use the differential form of the Maxwell equation to derive the wave equation, and then by solving the wave equation, we will get the solution of the EM wave. So yeah, but if you don't know how to derive the wave equation and how to solve the wave equation, you'll feel like chapter 33 when we talk about the EM wave, then it just like pump up many formulas, which is with no reasons. So I will supplement all those parts related to the EM wave. And also for this textbook, we do not talk about D, but of course in magnetism, we will also define what is D. But yeah, of course, some of you are ECE students, so I suppose you you will study the electromagnetism maybe in the next semester. So yeah, so later on you in the electromagnetism course, so you will face this kind of notation. But yeah, in this semester we don't really go deep into this part. Okay, so this is the first title of the first topic about in this chapter, which is about the electric flux. Electric flux. So it's here it says Gauss law relates the electric field at point on a closed Gauss surface. So in this textbook, we usually call a closed surface to be a Gaussian surface. So later on, we only call it Gaussian surface to the net charge enclosed by the surface. So actually, Gaussian surface is a closed surface, which means 封闭曲面 closed surface. Okay, which means that you cannot find a hole for the surface, which is for example, a complete sphere is a closed surface. For example, a cube is a complete surface. But if a cube you remove one of the side, then it is not closed. Or for example, if you have a bottle, then it is a closed surface. But if you open the bottle, then if a face, then you can pull in some water, then it's not closed surface. So which means that yeah, cold. So this is a definition of a closed surface. And for the Gauss law, we always talk about closed surface. So yeah. So here is a demonstration for the Gauss law. But before talking about the Gauss law, it just tell you what is electric flux. This is not so rigorous definition, but just a visualized explanation. Okay, so here it says, if we have a charge plus Q in the middle, plus Q, if it is a positive charge, it will of course generate the E field pointing outward. And if the charge is Q, maybe we can draw 8 arrows pointing outside. Because in the physics chapter, we know if the electric field line is denser, then which means that the electric field is stronger at that part. Okay, so we predefine if it is plus Q, we have 8 arrow here. So similarly, if we have plus 2Q, then we will draw 16 arrows pointing outward. Of course, it is a positive charge, is pointing outward. But here, this is plus Q, we have 8 arrows. And then if it is plus 2Q, then we will have 16 arrows. Okay, and then for this one, if we have a charge of a negative 5Q, this is a negative charge, so the electric field line will pointing towards the negative charge. And as much as the magnitude is 0.5, so we only have 4 arrows pointing to the charge. Okay, so here we try to do something is we try to draw a circle. Of course, it is a 3D shape, should be a sphere, but when we try to draw it on a paper, so it just look like 2D. So here we only draw a circle here. So here, if we draw a circle, then there will be 8 arrows going through this circle. And of course, this arrow are pointing out of the circle. And similarly here, we draw a circle, then there will be 16 arrows going through and going out of this region. And here we will have 4 arrows going in. So this is a visualized explanation for the electric flux. We try to calculate how much E field going through a surface. Electric flux can be defined for open surface, but yeah, for when we apply the Gauss law, it must be applied to a closed surface or a Gaussian surface. But here, this is a visualized explanation for how to count the E field going through a surface. So here is the mathematical definition for the electric flux. So of course we need to use some calculus notation to really define it. And here, of course, we will have electric flux d phi for a small area, d phi for a small area. If it is not a small area, maybe for a uniform E field, you can try to write it as a phi equals E dot A, something like this. If E is uniform over the surface, maybe you can learn something like this in the high school physics. You have already learned something like this in the high school physics for uniform E field. But here, of course, when we talk about non-uniform E field, then we need to use the calculus notation, the derivative or the differential form. Okay, so before we talk about the definition of the electric flux, we will define what is an area vector first. So the area vector is of course a vector. So this is written as dA vector for an area element. Okay, so it is a vector. Of course, it has a magnitude and direction. So yeah, so on the surface is a vector that is perpendicular to the element. So here, the area is a vector. So it has magnitude and direction. So the magnitude is easier to understand. The magnitude of the area vector will be the area itself. So the magnitude equals to the area dA. So for example, if we consider dA is like this, so it's like a rectangle. Of course, it's like a parallelogram, but yeah, actually this is x-axis, y-axis, and maybe we have some z-axis somewhere. But actually, it's a rectangle. It's a rectangle, but in a 3D way. So yeah, try to accept it as a rectangle. Okay, so the area of this rectangle will be the magnitude of the area vector of this area. Yeah. Okay, so dA, and then the direction will be the direction perpendicular to the element. So suppose this is a small area, then we can regard it as a plane. Maybe for curvature, when you can try to separate into small segment or small pieces, so that you can regard that part. Every part is a plane. Is on a plane. Okay, so you can try to draw a line perpendicular to it. Okay, so for this one, you can draw a line perpendicular to it. So this is the direction of dA or delta A. Yeah, so you may say there are two directions perpendicular to this surface. One is pointing to the left, and one of it is pointing to the right. I would say if it is an open surface, then either direction will be okay. But if it is a closed surface, then we'll tell you only one direction we will overuse. Okay, but maybe in the next pages we will talk about the definition of the direction. But yeah, for open surface, just like we have this one, you can either determine. But of course, you need to keep the direction, the definition of the direction. Otherwise, you may make mistakes for the plus or minus sign. Okay, so here is the definition of the area vector. Okay, so the direction is perpendicular to the element. The magnitude is equal to the area. So this is the definition of the dA. And then the electric flux for this small area will be E dot dA. For example, if the E field is pointing to this side, and then you try to calculate the dot product of the E and dA, and here is the delta A. Okay, so E dot dA, the magnitude will be the magnitude of E times delta A or dA, and then times cosine theta. It's related to the angle between the E field and the area vector. So this is the electric flux. And of course, electric flux is a scalar. This is a scalar. And you can clearly see it here is dot product. After finishing the dot product, it becomes a scalar. Okay. So yeah. So it says here A for A, an electric field vector P is small square patches of a flat surface. If the E field is if parallel to the surface, then yeah, there will not be any electric flux. For example, for this one, it's like, or maybe we can say if theta is 90 degree, then cosine of theta will be 0. Then it implies that the delta phi or d phi will be 0. So if the E field only has the component parallel to the area, then the electric flux will be 0. Okay, so next, so this is the complete definition for the electric flux. So now we can find the total flux by integrating the dot product over the full surface. The total flux through a surface is given by phi equals integration of E dot dA. Okay, so suppose we have a curvature like this, like a heart, and then of course it is a curvature, then it is not a plane like a cube or whatever, but we can try to cut it into many small pieces, so that for every small pieces we can regard it as a plane, and then we can try to use the definition as I mentioned in the previous page. Then you add all of them together, because all of the d phi, which is like integration of d phi, because all of the d phi are scalar, then we can just add them together to form the whole thing, to form the whole phi for the surface. So here it refers to the total flux. This definition is for a surface, not necessarily closed surface. It can be a open surface, like for example, if we have if we have a surface, this is the surface we consider, and then the E field is like this, maybe not so uniform, then we can of course cut this surface into many small parts, and we try to calculate. For example, this part, we have the E field pointing this way, and then we can define maybe all the vector are pointing to the right side, or the dA point to the right side. Yeah, of course, for the same surface, you need to have a unified direction for the, of course, not necessarily point to the same direction, but at least all the dA point to the right side, or all the dA point to the left side. You cannot have some dA point to the left side and some of the dA point to the right side. It's not okay. Okay, so but here we can try to determine d phi piece by piece. Then we can get d phi equals E dot dA. Of course, numerically, is it feasible? We can determine d phi piece by piece, and then finally we add all of them together to find the total electric flux for a surface. So it's called total flux phi, or even though these two phi have the same symbol, but yeah, this is total flux. So this is a simple integration sign. Okay, so one point to note is that the SI unit here is nm squared over c. Okay, so we can we don't really need to remember too much, because for the E field, the SI unit is n over c, and then for the area, the SI unit is m squared. So we multiply them together, so we have m squared over c. So it's easy to derive it out from the basic SI unit. Okay, so here we have another definition called the net flux. Okay, through a closed surface. So here is only for the closed surface, so which is used in Gauss law. Okay, it is given by phi equals almost the same thing, but here we have a circle here. This circles means we do the integration for the closed surface, or maybe for closed contour for the line integral. Of course, in chapter 29, when we learn about the Ampere's law, we will have the closed line integral for the E field, and also for the chapter 30, we'll learn Faraday's law, which is the closed line integral for the E field. But here, this circle means we do the surface integration for the closed surface. We do a closed surface integral, E dot dA. Okay, so here we will talk about the direction of the net flux. We cannot determine the direction by our own for the dA and also the flux. Yeah, so here it says phi is larger than 0 if the flux is flowing outward, and phi is less than 0 if the flux is flowing inward. And here also the dA will be pointing out of this closed surface. So for example, maybe here dA is pointing outward rather than pointing inward. For this case, you can either determine both directions are perpendicular to this piece, so you can determine the direction of dA by your own. But here, for closed surface, we always define the dA direction to be pointing out of this closed surface. Okay, so yeah, so dA pointing to the outside. For example, this part is pointing to this side, and for this one is pointing to this side. It never pointing to the inside part of the surface. Okay, so if so it says if so if this theta is less than 90 degrees, then phi will be larger than 0. Phi will be larger than 0. If this is a right angle between the E field and dA, then phi will be 0. And if this phi is larger than 90 degrees, then it will be the phi will be less than 0. Okay, so here the net flux means 径通量. Okay, so it somehow counts how much E field is pointing outside or inside the surface, something like that. The physical meaning is something like this. Okay, so yeah, so the net flux is written like this. Okay, so here we try to use so we try to draw it out like this. Suppose this is the Gaussian surface. This is the Gaussian surface we define. And if phi is positive, for example, if we have a charge Q inside, then the E will pointing outward. Okay, so and for the dA, it always perpendicular to the surface and pointing outside. So dA will be pointing this way, dA pointed this way here, dA pointed this way here, dA pointed this way here. And of course, for this one, dA point to here. I don't try to draw too much, yeah, but I hope you can understand. dA always point to the outside. So you can see E and dA points to the same direction, so that E dot dA is a positive value. So it turns out, or you add all the positive value, then the net flux will be a positive value also. But of course, when you try to separate the surface into many small parts, not necessarily all the d phi have the same sign. Maybe some of them will be positive and some of them are negative. But usually when we try to use the Gauss law, we try to find some symmetric, which makes most of the, or I should say, which makes almost all the d phi will be the same value, so that we don't need to calculate anything. Okay. But generally speaking, when you try to define an arbitrary Gaussian surface, it doesn't necessarily that all the d phi are positive or all the d phi to be negative. Maybe some of them are positive, some of them are negative, and then some of them cancel out to see whether the net flux is positive or negative. Okay, so for this part, maybe if we have a negative charge inside, then it will generate some E field pointing inside. And here, still dA pointing outside. Doesn't relate it to the charge. dA always pointing outside. dA always pointing outside or outward. Okay, so here you can see dA and E points to the opposite direction. So you can see d phi equals E dot dA is a negative value. So you add up many negative values. So the total flux or the net flux will be negative value. So we can see the E field is tends to flowing into this surface, and then for this case, the E field tends to flowing out of this Gaussian surface. Okay, so far any question? If you have any question, try to raise it, and maybe we can have a 10 minutes break.